Good afternoon, everyone. I hope that you've been having a great week so far. Once again, I apologize that I couldn't be available yesterday for any help. Today, what we're moving on to is lesson 30.16, which deals with analyzing rational functions. And this lesson can be found on page 2 of your current lesson handout. To begin with, a very basic definition is that a rational function contains the independent variable, which is x, in the denominator. So any function that has over x, or over 2x, or over x squared minus 1, or over any expression that has x in it is a rational function. Because denominators are never allowed to be 0, and because there are x's in the denominators of rational functions, there might be values of x that make the denominator equal to 0. And those values of x are called non-permissible values of x. As a warm-up, we're going to look at two rational functions, f of x and g of x. F of x is x squared minus 8x plus 15 all over x minus 2. G of x is x squared minus 3x plus 2 all over x minus 2. They both have denominators that contain x, and that's why they're called rational functions. So what is the non-permissible value for x in f of x? So how do we find the non-permissible value for f of x? We look at the denominator, which is x minus 2, and remind ourselves that x minus 2 cannot be equal to 0, which means that the number that makes x minus 2 0 is non-permissible, and that number is 2. And we would do the same thing for g of x. I don't think you need to write it twice, but g of x also has a denominator of x minus 2, which means x is not allowed to be 2. The reason x is not allowed to be 2 is if x were 2, both of these functions would have 0 in the denominator, and that's not allowed. You're not allowed to divide by 0. Now what we're asked to do is sketch the graphs of f of x and g of x using a graphing calculator. And these are going to be very rough sketches. We're not too interested in the finer details of the graphs so much as we are interested in what's going on close to that non-permissible value. All right, so f of x is x squared. Now we're going to need to put a set of brackets over the entire numerator. X squared minus 8x plus 15, and then divide by, and we need a set of brackets around the denominator as well, which is x minus 2. And I'm going to choose to go zoom 6, which is standard. And we get this picture of the graph. And I'll come back to that in a second, but let's also graph y equals g of x, which is x squared minus 3x plus 2, divided by, in brackets, x minus 2. And again, I'm going to choose to go zoom 6. And what we see for the second graph is apparently a line. So this rational function looks like a linear function, but I'm going to tell you it's not a linear function. A linear function is a straight line that extends forever in both directions, and this line has a tiny, tiny missing piece to it. If I were to go to my table and take a look at different x coordinates, when I get to x equals 2, I get an error. And what that means is there is no point at x equals 2 on g of x. If I were to go back to my graph now and hit trace 1 and go equals, it tells me when x is 1, the y coordinate is 0. If I went trace 3, it tells me that when x is 3, y is 2. If I try trace 2, I get nothing. And that's because at 2, there's what we call a hole in the graph. In order for you to see the hole, and this isn't always going to work, but it works in this case, if you choose zoom decimal, which is zoom 4, you get that little hole in the line. Now, rather than me drawing them, we do have a graphing calculator. So there's the sketch of f of x. Here is the sketch of g of x. The actual graph of f of x has two pieces to it. It has a piece that looks like this, and it has another piece that looks like this. That vertical line that your calculator is plotting in there is actually an asymptote. It is a line that the graph gets closer and closer and closer to. But it is not actually part of the graph. The graph is in red. The blue dotted line is what's called an asymptote. And no matter how close that red gets to the blue line, it will never reach that blue line, because on that blue line, x equals 2. Right? The equation of this line is x is equal to 2. But x is not allowed to be 2 in either of our functions. Over here, x is 2 at this point, and there is a little tiny hole in the graph. And what we want to focus on today is how you can tell whether a non-permissible value is going to give us a vertical asymptote or a hole. So what's the difference between the two graphs in terms of the non-permissible value? F of x has a vertical asymptote at x equals 2. G of x has a hole at x equals 2. And a hole is sometimes referred to as a point of discontinuity. Simplify each function and write a rule for explaining your answer. So this is where we learn how we can figure out whether it's going to be a vertical asymptote or a hole. Well, when you simplify a rational expression, that involves factoring first. This goes back to Math 20. Everything about rational expressions is accomplished by factoring. And it turns out that each of these numerators is factorable. We are looking for f of x, we are looking at two numbers that multiply to give 15 and add to give -8. That would be -3 and -5. And for g of x, we are looking for two numbers which multiply to give 2 and add to give -3, which would be x minus 1, x minus 2. Here's the rule. If the factor that's in the denominator that creates the non-permissible value, if that factor cancels with an identical factor in the numerator, then at that non-permissible value, there will be a hole. If the factor that creates the non-permissible value, x minus 2 in this case, does not cancel, then the value of x that comes out of that non-permissible value will create a vertical asymptote. By the way, when we write this function for g of x, and we cancel those x minus 2's, if I write x minus 1, that is not correct. I need to also say that x can't equal 2. Because if I graph x minus 1, it's going to be a straight line with no holes. I need to include that hole. So what is the rule? If the factor doesn't cancel, then you have a vertical asymptote. If the factor cancels, then you have a hole. That's it. That's the rule. Now, one final thing here. If we want to find out where that hole was vertically, so if I want to know what this y coordinate of the hole is, what I can do is take the x coordinate, which is 2, and even though I'm not allowed to use 2, if I put 2 into whatever is left after I've canceled, then I will get the y-coordinate of the whole. So the y-coordinate of the whole is found by taking the x-coordinate of the whole and putting it in for x in the expression that you're left with after you cancel, which means the y-coordinate of the whole in this example would be 2 minus 1. So our whole would have coordinates of 2, 1, because when I put 2 in for x here and I subtract 1, I get 2 minus 1, which is 1. Okay, what are the domain and range? Well, the domain of each function is that x cannot be equal to 2. Now, don't forget g of x has a whole. G of x was a line with a whole, and the coordinates of that whole were 2, 1. So if x can't equal 2, then y cannot equal 1 for that function. And for the range of f of x, since it turns out that the range of f of x has nothing whatsoever to do with what we're learning today, I'm going to tell you that we're not going to worry about it. The bottom line, what you need to know, is that if the factor that produces the non-permissible value cancels, then the x-coordinate that is non-permissible becomes an x-coordinate of a whole, and the y-coordinate of the whole can be found by putting that non-permissible value of x into whatever is left after you cancel. If the factor that produces the non-permissible value does not cancel, then there is a vertical asymptote at that point. So analyze each function in terms of non-permissible values. In order to analyze these functions, you need to factor everything completely. So we have x times x plus 2 in the numerator, and the denominator is non-factorable. So when we talk about non-permissible values, we are always looking at the denominator. We're asking ourselves, are there any values of x that make the denominator equal to 0? Well, since x squared is always going to be a positive number, when you add 4 to it, you can never get 0. In other words, for example A, there are no non-permissible values. There's no value of x in the universe that can make the denominator 0 here. For the second one, g of x, we factor everything completely. I can factor a common factor of x out of the numerator. The denominator is a difference of squares. We can see that there are non-permissible values here of x equals negative 2 and of x equals positive 2 because of the two factors in the denominator. Since the x plus 2's cancel, that means that the non-permissible value of negative 2, which came out of the x plus 2, is a whole. We're going to have a whole at negative 2 comma something. Because the x minus 2 did not cancel, that means the positive 2 is going to be a vertical asymptote at x equals 2. The only thing we have left is to find the y-coordinate of the whole. Well, the y-coordinate of the whole is found by putting the x-coordinate of the whole in for x in whatever is left. So when we take a look at what is left after I cancel, it's x over x minus 2. So I need to take negative 2 divided by negative 2 minus 2. That gives me negative 2 on the top and negative 4 on the bottom, which gives me 1/2. So this graph of this function would have a whole at negative 2 comma half and a vertical asymptote at 2. And you could feel free to use your graphing calculator to confirm these things. C, we're going to start by factoring things to see if anything cancels. We can see by looking at the denominator that we have a non-permissible value of x equals 4. What will there be at x equals 4? There will be a vertical asymptote because the factor that produces the non-permissible value of 4 does not cancel with a factor on the top. This x minus 4 is what leads us to the x equals 4 for the non-permissible value, and there's no x minus 4 on the top to cancel. D, again, you're always factoring. I can take out an x and be left with x plus 2, and it's over x plus 2. The fact that there is a denominator factor of x plus 2 tells me that I have a non-permissible value of x equals negative 2. What will there be there? There will be a hole, and it will have coordinates of negative 2, comma. Well, how do we determine the y coordinate? We cancel the factors, and we put in for x the x coordinate of the hole into whatever is left. And the only thing that's left is this x, which means we get a y coordinate that's equal to negative 2 as well. Match the following graphs with the 3 functions. In order for us to do this, we have to factor everything completely. Function a of x factors into x times x plus 2 over x plus 2, x minus 2. The function b of x factors into 2 times x plus 2, and the denominator doesn't factor at all. And c of x is 2x over x plus 2, x minus 2. When you take a look at b of x, the equation for b of x, the denominator in b of x is x squared plus 1. And there is no value of x in the universe that makes that equal to 0, which means that b of x has no non-permissible values. And what that tells us is the graph of b of x has to be the graph that is defined everywhere. This must be b of x. It has no breaks in it. When we take a look at c of x has a non-permissible value of negative 2 because of this factor, and a non-permissible value of positive 2 because of this factor, and neither of those factors cancel, which means we're going to have 2 vertical asymptotes. That tells us that c of x must be graph 1. When you take a look at a of x, there is a non-permissible value at 2, and the x minus 2 that produces that non-permissible value doesn't cancel, so you get a vertical asymptote at 2. And we have a non-permissible value at negative 2, and because the x plus 2, which creates the non-permissible value of negative 2, does cancel, we get a hole, and that means that the middle graph is a of x. Let's try this again. You always want to factor things completely. The top of k of x does not factor, but the bottom factors into x minus 2, x plus 1. Well, let's just find that graph right now. K of x has 2 non-permissible values and neither one of them cancel, which means it's going to have 2 asymptotes. We don't even need to go further to know that this is k of x. L of x is x minus 1 on the top and then x plus 1, x minus 1 on the bottom. Well, L of x has 2 non-permissible values, but one of those non-permissible values cancels, which means of the 2 non-permissible values for L, one is a hole, one is an asymptote. Graph 1 must be L of x. We take a look at M of x. It factors into x minus 3, x minus 2 over 3 minus x. The 3 minus x will cancel with the x minus 3, which means you're going to have a hole at 3, and that tells us that this is m of x. All right, one last example that we want to do here, and this is just to show you one other little rule. We're given a graph of a rational function and we're asked to determine the equation of the function. So I'm going to start building the equation of this function by putting factors in the denominator that will create the non-permissible values. You can see a non-permissible value here at -2. That must mean we have to have x plus 2 in the denominator. You can see a non-permissible value at 3, which means we must have x minus 3 in the denominator. And since the whole is produced because of the x minus 3, we need another factor of x minus 3 on the top to cancel. Because that's the rule. The whole will be there if the factors cancel. Now there's one other thing that you need to remember, and it's this. If you have an x-intercept, then that will have a factor in the numerator. This is the answer to the question. To summarize this lesson, when you have a factor in the numerator and denominator of a rational expression, that will show itself on a graph as a whole in the graph. When you have a factor in the denominator but not in the numerator, that will show it to you on a graph as a vertical asymptote. When you have a factor in the numerator but not the denominator, that will show it to you on the graph as an x-intercept. So factor in both is a whole, factor in the bottom is a vertical asymptote, factor in the top is an x-intercept. There's your assignment dealing with this lesson, page 452, 5, 6, and 7, and problems 1 to 3 on the next page. I hope that lesson made sense, and I hope you have a fantastic rest of the day and a great weekend. We'll talk to you guys soon. Take care.